So next I am going to discuss a problem based on the special case I have discussed in the previous class. This is the problem number 2 in this chapter, center of mass and conservation of linear momentum. Look at the screen for the problem. I will once read out the problem. So in case you want to try it yourself first, you can take a pause and try the problem. Otherwise, I can look at the solution I will be discussing for the problem. So once first I read out the problem. A 10 kg boy is standing on a boat of mass 40 kg, floating in water, such that the boy is 20 meters from the shore. The boy walks linearly 8 meters on the boat towards the shore and stops with respect to the shore. Then how far the boy will be from the shore? Within bracket, neglect friction between the boat and water. In case you are interested to try it yourself first, you can take a pause and try the problem. Otherwise, you can just listen to the first concentrate to listen to the solution which I am going to discuss. I will be also giving a similar problem in the assignment in my next class. So here we consider the boy and the boat together as one system. So in case you want to try, you can take a pause and try. I am going to show the answer also first, then I will discuss the solution. Answer is 13.6 meter. So now I am going to discuss the solution for this problem. Here the mass of the boy or person standing on the boat, which are denoted by small m in the earlier discussion, that is given to be 10 kg. The mass of the boat denoted by m2 or capital M in the earlier discussion in the earlier class is a special case, that is given to be 40 kg. It is given that a man walks 8 meters on the boat. That means magnitude of the relative distance or relative displacement. Magnitude of the relative displacement of the man with respect to the boat is 8 meters. Initially the man is at a distance, I mean the boy is at a distance of 20 meters from the shore. Let x1 denote the initial distance of the boy from the shore. So here we consider both the boy and the boat together as one system. Net acceleration system is 0. Initially both the boy and boat are at rest. So initial velocity center of mass system is 0. And based on same reasoning which I have discussed in the previous class, you can say that center of mass system will be at rest. So if you remember the conclusion I have discussed in my previous class for the special case 3, the last special case I discussed in the previous class, the magnitude of the actual displacement of the boat or distance moved by the boat in the opposite direction, away from the shore, given by small m by capital M plus small m into magnitude of the relative displacement of boy with respect to the boat. Here small m equal to 10 kg, capital M equal to 40 kg. Magnitude of the relative displacement is 8 meters. So magnitude of the actual displacement of the boat with respect to the shore or with respect to stationary observer on the shore is 1.6 meters. As I discussed in the previous class, in the last special case in the previous class, the magnitude of the relative displacement of the boy with respect to the boat is equal to the magnitude of the actual displacement of the boy plus magnitude of the actual displacement of boat. So magnitude of the relative displacement is 8 meters. Magnitude of the actual displacement of the boat is 1.6 meters. So magnitude of the displacement of the boy with respect to the stationary observer on the shore will be comes out to be 6.4 meters. If x1 is the initial distance of the boy from the shore and x1 dash is the new distance of the boy from the shore, choose the origin at the shore. The magnitude of the actual displacement of the boy toward the shore is equal to x1 minus x1 dash. That is 6.4 meters equal to 20 meter minus x1 dash. So x1 dash is the new distance of the boy from the shore. That will be equal to 20 minus 6.4 meter. That comes out to 13.6 meter. This is the answer. If you want to copy down the solution of the problem, you can take a pause and copy down the solution of the problem. Next, I am going to discuss an alternate method for the same problem, because some of the students may not be able to recollect this result which I have directly put here. Because if you remember the discussion I have already done for the special case, last special case previous class, then you will be able to use this formula directly. But some of the students may not be able to exactly recollect the conclusion of the special case. So, I'd like to also therefore discuss the usual way one is expected to solve in case you are given this problem or similar problem in board examinations. Next, I am discussing the same problem by the alternate method. This alternate method is particularly, you may have to follow this alternate method in case by chance similar problem you are given in board examination. Of course, in the board exam, usually such standard questions are not given. More simpler questions are given. But still, you must know the usual method, how it is worked out, as we are supposed to work it out in the subjective exam and or in board examination. We choose some fixed point at the shore as origin. Let's see one with the initial point center of mass of the boy. And initial distance of center of mass of boy from the shore denoted by x1, that is given as 20 meter. Let C2 be the initial position of center of mass of the boat. Let D be the initial distance between C1 and C2. The boy walks on the boat toward the shore through some distance. So let C1 dash denote the new position of the center of mass of the boy from the shore. I mean C1 dash the new position center of mass of the boy after he walks on the boat and stops. Let x1 dash the new distance of the boy from the shore. Some students may commit the mistake of subtracting 8 meters from 20 meters. They may think that the answer is 12 meters. When the boy begins to walk on the boat toward the shore relative to the boat will also begins to move, but in the opposite direction. The boy stops on the boat will also stop moving. Let C2 dash denote the new position center of mass of the boat. That means distance from C2 and C2 dash gives you the magnitude of the displacement of the boat I denote by S2. Distance between C1 and C1 dash gives you the magnitude of the displacement of the boy denoted by S1. The boy walks 8 meters on the boat relative to the boat. That means the distance between the center of mass of the boat and center of mass of the boy will increase by 8 meters. Therefore, new distance between center of mass of the boat and center of mass of the boy becomes D plus 8 meters. D is the initial distance between the center of mass of the boy and center of mass of boat. Now, using the same analogy, I mean same reasoning which I have discussed in the special case, last special case of the previous class, because no external forces are acting on system. I mean net external force on system is 0. The total weight of system is balanced with the upward force of balancing. And center of mass of system is initially at rest, so continues to be at rest. So center of mass of system is at rest. Therefore, distance of center of mass system from the origin will be the same in both the cases. Xm dash equal to Xm. Xm is the initial distance center of mass from the origin. You can write M1 X1 plus M2 X2 by M1 plus M2. Xm dash is the new distance of center of mass from the origin, which you can write it as M1 into X1 dash plus M2 into X2 dash by M1 plus M2. M1 plus M2 can cancel. X2 dash is a new distance center of mass of the boat from the origin. So you can write from the situation shown in the figure, you can write M2 into X2 dash minus X2 equal to M1 into X1 minus X1 dash. X1 is the initial distance of buoy from the shore, X1 dash is the new distance of the buoy from the shore. So X1 minus X1 dash gives you the distance moved by the buoy toward the shore with respect to station observed on the shore. X2 is the initial distance of the boat from the shore. X2 dash is the new distance of the center of mass of the boat from the shore. So X2 minus X2 dash X2 dash minus X2 gives the distance moved by the boat with respect to station observed. Mass of the boat is given to be, that means here you can write M2S2 equal M1S1. M2 is equal to 10 kg here, 40 kg here, mass of the boat. M1 equal to 10 kg. So you get S2 equal to S1 by 4. S1 is the magnitude of the displacement of buoy. Actual displacement of buoy with respect to station observed on the shore. S2 is the magnitude of the actual displacement of boat. You can observe from the figure distance between C1 dash and C2 dash. In second case is D plus 8 meters. That is equal to distance between C1 dash and C1, that is S1 plus D plus S2. D gets cancelled, so you get S1 plus S2 equal to 8 meters. You can substitute S2 equal to here S1 by 4. So you get S1, if you simplify this yourself, S1 you get 4 by 5 times 8 meters. Or S1 is 6.4 meters. S1 is the magnitude of the actual displacement of the buoy towards the shore with respect to station observed on the shore. Magnitude of actual displacement buoy towards the shore, you can write initial distance of the buoy from the shore minus final distance of the buoy from shore. X1 dash is the final distance of the buoy from the shore. That is equal to X1 minus S1. X1 is 20 meters, S1 is 6.4 meters. So you get X1 dash equal to 13.6 meters. That's the answer. Now, in case you are interested to copy the solution of the problem with alternate method also, you can copy the solution of the problem. You can take a pause and take your own time to copy the solution of the problem. Next, I am going to discuss about center of mass reference frame. So earlier I have discussed that the vector sum of momenta of all the masses of all the particles of a system of n discrete point masses, that is given by sigma as I discussed earlier, the vector sum of moments of the masses of all the particles of system with respect to origin of a coordinate system, because the product of total mass of system and position vector of center of mass of system, and vector sum of linear moment of all the particles system or total linear order system is equal to product of total mass of system and velocity center of mass system. The frame of reference or coordinate system in which center of mass is the position of center of mass is taken as the origin of coordinate system is called center of mass frame or center of mass reference frame. The coordinate system or frame of reference in which we choose the position of center of mass as the origin of the coordinate system is called center of mass frame or center of mass frame of reference. So in this center of mass reference frame, or in short we write CM reference frame, center of mass is at the origin. Center of mass is at the origin of the coordinate system. So for the distance of center of mass from the origin is 0, so RCM will be 0. Or RCM bar is 0 bar. So and velocity center of mass will be 0. That means the last center of mass relative to center of mass will be obviously 0. So the vector sum of moments of the mass of all the particles of system with respect to center of mass system as origin becomes to be 0. And vector sum of linear moment of all the particles of system relative to center of mass system will also be 0. So vector sum of the moments of the mass of all the particle system with respect to the center of mass system will be 0. And vector sum of linear moment of all the particle system with respect to center of mass will be 0. Don't try to write the notes right now. Just stop writing and listen to me. I will be showing you the notes for the center of mass frame separately later. Just concentrate to listen. So vector sum of the moments of the mass of all the particles of any system with respect to center of mass system as origin will be 0 vector. And vector sum of linear moment of all the particles of any system with respect to center of mass system as origin will be 0 vector. Suppose if you consider system of two particles, because you have a good number of questions based on system of two particles. If you consider system of two particles of mass m1 and m2, just listen here. Don't write the notes now. Let us suppose the first particle of mass m1 is moving with velocity v1 bar with respect to stationary observer on the earth or with respect to laboratory frame of reference. Second particle of mass m2 is moving with a velocity v2 bar with respect to stationary observer on the earth or with respect to laboratory frame of reference. The velocity center of mass system of the two particles with respect to stationary observer on the earth or with respect to laboratory frame of reference given by m1 v1 bar plus m2 v2 bar by m1 plus m2. So relative velocity of m1 with respect to center of mass denoted by v bar subscript 1c, that is equal to v1 bar minus vcm bar. You can substitute vcm bar equal to m1 v1 bar plus m2 v2 bar by m1 plus m2. This can be simplified further you get relative velocity of m1 with respect to center of mass is equal to m2 into v1 bar minus v2 bar by m1 plus m2. The same way, relative velocity of m2 with respect to center of mass of the system denoted by v bar subscript to c equal to v2 bar minus vcm bar. VCM bar you can write m1 v1 bar plus m2 v2 bar by m1 plus m2. This you can simplify this. You get m1 into v2 bar minus v1 bar by v1 plus v2. The mass m1 m2 are always positive and scalars. So m2 by m1 plus m2 is a positive scalar. The same way m1 by m1 plus m2 is a positive scalar. So direction of the v bar subscript 1c. That means the direction of the velocity vector of m1 with respect to center of mass is in the direction of the vector difference v1 bar minus v2 bar. The direction of v bar to c. That means direction of the velocity vector of m2 with respect to center of mass in the direction of the vector difference v2 bar minus v1 bar. Suppose if v1 bar is not equal to v2 bar. I mean, if the two particles of mass m1 and m2 are moving with different velocities with respect to stationary observed on the earth, then direction of v bar to c will be is opposite to the direction of v bar 1c. So direction of the relative velocity of center of m2 with respect to the mass will be opposite to the direction of velocity of m1 with respect to center of mass. That means if 2-point mass m1 m2 are suppose moving with unequal velocities or different velocities with respect to a stationary observed on the earth or with respect to the laboratory frame of reference, then with respect to center of mass frame or with respect to center of mass, the two particles appear to move in opposite directions. Suppose if the two particles are moving with equal velocities with respect to stationary observed on the earth, I mean actual velocities of two particles are equal, then you can observe that if v1 bar equal to v2 bar, then v1c will be 0 and v2c will also be 0. Then velocity of m1 with respect to center of mass is 0 and velocity of m2 with respect to center of mass will also be 0. That means with respect to center of mass, both the particles appear to be at rest or stationary if they are moving with equal velocities with respect to stationary observed on the earth. You can arrive these conclusions by another approach also. So as I discussed before, in the center of mass frame, I mean the center of mass reference frame, the frame of reference in which we choose the position of center of mass system as the origin of coordinate system, the vector sum of linear momenta of all the particle system with respect to center of mass system will be 0. If you consider a system of two particles, then total linear momenta of the system of the two particles with respect to center of mass will be with respect to center of mass of the two particles will be 0. That means p bar 1c plus p bar 2c is 0. P bar 1c represents the vectors, I mean the linear momentum vector of the first particle of mass m1 with respect to center of mass. P bar 2c represents linear momentum vector second particle of mass m2 with respect to center of mass of the system of the two particles. That means if you consider system of two particles, then with respect to center of mass system of the two particles, The two particles appear to move in opposite directions with same magnitude of linear momentum. So P bar subscript 1c can write m1 into V bar subscript 1c. P bar subscript 2c can write m2 into V bar subscript 2c. That means the relative velocity of m2 with respect to center of mass will be opposite relative velocity of m1 with respect to center of mass. The two particles are moving with different velocities with respect to station observed on the Earth. Next, I am going to show you the notes for the same discussion which I have just now discussed. So those who are writing the notes or want to copy the notes, you can get ready with your notebook and pen. So next, I am going to summarize the discussion I have just done about center of mass frame. Look at the screen here. So those who are writing the note, they can get ready with your notebook and pen. So in the center of mass reference frame, RCM bar equal to 0 bar, VCM equal to 0, and FCM equal to 0. So I am going to show you the notes for center of mass frame now. You can start writing the notes for center of mass frame. In the center of mass reference frame, RCM bar equal to 0, VCM bar equal to 0. That means in general, sigma mi RA bar, when I varies from 1 to n equal to capital M into RCM bar, and capital P bar equal to capital M into VCM bar. So in the center of mass reference frame, RCM bar is 0 bar and VCM is 0. Therefore, sigma mi RA bar becomes 0 and P bar becomes 0. Come on, finish copying this. So in case you need more time to copy this, you can take a pause and take your time. In COM reference frame, that means center of mass reference frame, the vector sum of linear momentum of all the particle system is equal to 0 bar. That's one conclusion which you have to remember. A system of two particle center of mass frame, P bar equal to P bar 1c plus P bar 2c. P bar means total linear momentum system of the two particles. P bar 1c is the momentum vector of first particle with respect to center of mass system of the two particles. P bar 2c is the momentum vector of second particle with respect to center of mass system of the two particles. So vector sum of linear momentum of all the particles of any system with respect to center of mass system as origin will become out to zero vector. That means P bar 2c is equal to minus of P bar 1c. Can write M2 V bar subscript 2c equal to minus M1 into V bar subscript 1c. Of course, here understood that V bar subscript 1c represents relative velocity of first particle of mass M1 with respect to center of mass system of the two particles. V bar subscript 2c represents relative velocity, a second particle of mass M2 with respect to center of mass system of the two particles. So if V1 bar is not equal to V2 bar as explained previously, then V bar 2c is opposite to V bar 1. V1 bar is the actual loss of M1 and V2 bar is the actual loss of M2. It means V1 bar is velocity of M1 with respect to station observed on the ground. V2 bar is velocity of M2 with respect to station observed on the ground. Come on, finish copying this part of the notes. In case you need more time to copy the notes, you can take a pause and take your own time. I'm going to just show the continuation to this. V bar subscript 1c equal V1 bar minus VCM bar. V bar subscript 2c equal V2 bar minus VCM bar. VCM bar is the actual loss center of mass system of the two particles with respect to station observed on the Earth. V bar 1c is the velocity of M1 with respect to center of mass system of the two particles. V bar 2c is the velocity of M2 with respect to center of mass system of the two particles. So if V1 bar equal to V2 bar, then V1c bar equal to V bar subscript 1 is equal to v bar, subscript 2 is equal to 0 bar. That means if both the particles are suppose moving with equal velocities with respect to station observed on the earth, then they appear to be at rest with respect to center of mass frame. So here same conclusion which I discussed previously I have given here. If two particles have different velocities with respect to station observer in the laboratory frame, then at the center of mass frame, the two particles appear to move in opposite directions. Come on, finish copying this. In case you need more time to copy this, you can take a pause and take your time. So in my next class, I am going to show you the assignment in center of mass and conservation of linear momentum. So before that, before showing you the assignment in center of mass and conservation of linear momentum, I would like to also once briefly discuss on how we find the position of center of mass of continuous bodies. So as I discussed earlier, if you consider a system of n discrete point masses, if you consider system of n discrete point masses, mean discrete point masses means when one point mass is separated from other point masses by finite distances, the next coordinate of center of mass of the system of n discrete point masses, we write sigma mi xi, where I varies from 1 to n divided by capital M, or we write it as m1 x1 plus m2 x2 plus m3 x3 etc. up to mn xn divided by capital M represents some of the masses of all the n particles of system. The same way we write bicoordinate center mass of system of n discrete point masses. We write sigma mi yi by capital M, where I varies from 1 to n, or m1 y1 plus, or bicoordinate center of mass system of n point masses or n discrete point masses, given by m1 y1 plus m2 y2 plus m3 y3 etc. up to mn yn divided by m1 plus m2 plus m3 up to mn. So when you consider continuous bodies, in case you have to find the position of center of mass of a continuous body where mass is distributed uniformly, may be distributed uniformly along the length of a rod or semicircular plate or semicircular ring, like that. So in such cases, this discrete summation is replaced by continuous summation. That means to find the position of center of mass of continuous bodies like a thin uniform semicircular ring or thin uniform semicircular plate or thin uniform rod, or a rod where you may be given the linear density of the rod to vary according to some equation. So that means in the case of continuous bodies, instead of discrete summation, we have to follow the continuous summation method. That means we imagine that the given mass to be divided, the body to be divided into large number of elementary masses, and each elementary mass is denoted by dm. That means if x comma y comma z denote the Cartesian coordinates of the center of mass of that elementary mass dm, the next coordinate center of mass of the body, the right integral x dm by capital M. Capital M is the total mass of body. we choose the limits of integration in such a way so that summation is carried out for the entire mass of the body. Similarly, y coordinate center of mass in the case of continuous bodies, we write integral y dm by capital. Z coordinate center of mass, we write integral z dm by capital. Like that. So in my next class, I am going to show you the assignment in center of mass and conservation amount of first assignment. I mean, first part of the assignment in center of mass and conservation amount. I will be showing you the 30 questions. I will not be discussing the solutions of these questions in the next class. In the next class, I will be just showing only the questions so that you can read each question, try to answer each question. Write your answers on separate paper, on a white paper. So I will be showing the questions one after another. After each question, I may give you little gap which may or may not be sufficient for you to answer the question. The gap is given keeping in view of those students who answer very fast. In case the time given or gap given is not sufficient for you to answer the question, you can take a pause and take your own time. You try to answer all the questions one after another, or try to answer as many questions as you are able to answer. At least we should become familiar with the questions. After showing all the 30 questions, and the last will be giving you the answers for all the 30 questions. In my next class, after that, I will be discussing the solutions of all these questions. Should not get discouraged or disappointed if you are unable to answer the questions in the assignment when I show you these questions. Some of the students may not be able to answer good number of questions. They may be able to answer only very few questions. But still you have the chances to improve if you have interest to improve and if you are serious to improve. In case you are too weak in answering these questions, I mean if you are unable to answer most of the questions in the assignment in center of mass and conservation momentum, when you read them for the first time, doesn't matter. You still first finish going through all the questions. Then you go through all the solutions which I discuss in my next class after that. After going through all the solutions, then again come back. I mean you take after going through the solutions, you take a gap. You can take a gap of 1 hour, or you can sit the next day. You can again start fresh. That means again start going through the assignment in center of mass and conservation remote, starting from beginning as if you are going through it for the first time. Then again you try to work out them second time. That means after going through solutions also you can make you should again work out the assignment freshly, so that now you will be able to answer most of the questions. So what is needed is, if any one of these questions or problems or similar questions or problems happens to come in future test papers or exams or final exams you write, you should be able to answer them correctly. Okay, in my next class I am going to show you the assignment in center of mass and conservation momentum.